Okay, so in a binary multiplier, it is a combinational multiplier as a logic circuit which is implemented to perform multiplication. Okay, so multiplicand is multiplied by each bit of multiplier started from least significant bit. Everyone knows the least significant bit and most significant bit now, right? Each multiplication forms a partial product. Okay, successful partial products are shifted one position to the left, and the final product is obtained from the sum of partial products. I hope that everyone knows a simple decimal multiplication. The same format will be applied for binary multiplier. So let me show the simple binary format. Don't by saying this, don't consider that it's more complicated. I will make much simpler. So, okay, let me start for understanding multiplication, simple multiplication, how we will perform. First step, okay, simple multiplication, how we will perform is, let us consider, let us consider 22 into 11. So I want to perform 22 into 11. For that, this one has to be multiplied with 1 into 2 and 1 into 2, and next this has to be multiplied 2 and 2. So you will be getting this, the final one. These are the partial products. This is your final product. So 4, 2. This is the process, right? So if there is one more product 1, so this will be written from here. So left to shift. So we already discussed, you will be having left to shift operation. Where is this left to shift? So are shifted, successful partial products are shifted one position to the left. Same like how we will do a binary uh, decimal multiplication. Okay. So the same process will apply for binary as well. So the same process will apply for binary as well. So consider 2-bit. So let me show before going for a. I want to take multiplicand and multiplier as 2-bit. Okay, yeah, I can say take 3-bit, 4-bit, 4-bit, 3-bit. It depends upon the question they ask. But I want to start with 2-bit. Okay, so 2-bit multiplicand, 2-bit multiplier I want to take. So here, let me start with these and what we have considered in this B0. Let me show. The same process need to be applied. No? So B0 as B0, B0, B1 as multiplicand and B. I will show here itself. Okay. So I don't say this much. Let me write here B0, B1. Okay. And A0, A1. Okay. So according to your knowledge, everyone knows us. This has to be multiplied with B0 and B1. So I am writing A0 multiplied with B0. Next A0 multiplied with B1. A0 multiplied with B1. Okay. Next this has to be multiplied with B0. A1 has to be multiplied with B1. So one bit position shifted left up. Okay. So here A1 B0. Next is A1 B0 completed, A1
B1.
B1. Okay. Next you need to get, these are your partial products, partial product 1 and partial product 2. You need to get final result. So for this what we need to do, this has to be taken as it is. So you will be considered as P0. So product terms. Okay. So before going for a product terms, you must know, given a multiplicand and multiplier, how many product terms will be the result. So product terms can be calculated as, consider this as M and consider this as N. So m plus n product terms will be there. So here we have a 2, n is all, multiplier is also n, also 2. So 2 plus 2 you will be getting 4. So you will be getting 4, you will be getting 4 product terms. You must know this. So how many product terms will you get means based on m plus n. M consider as multiplicand, n consider as multiplier. If you add both, you need to get what, 4. Okay. So this is your 4. So what we are doing in this case is, this I am considering as P0. Why? Because you will be taking this as it is in normal decimal multiplication also. So next is what? I need to do addition between these two. A0 B1 and A1 B0. I need to do addition, so that I will get what? so that I will get P1. Okay. Next, in order to get P2, this the output from this, a carry will be generated, right? So if you add 1 plus 1, you will be getting 0 as sum and carry as 1. So this carry will be forwarded here and will be taken these two operands. Will be taken these two operands, and if you add, you will be getting product P2. Okay, you will be getting product P2. Again, if you to add this two, you will be getting sum, you will be getting carry. Sum is considered as P2 and carry C2. This will be considered as P3. Okay, so I will show with an example so that you can understand clearly. Okay, so for that, first of all, in order to implement binary, multiplier, you must use AND gates. Why? Because there is an AND in between this and this. But before going to the AND gates, you must know how many AND gates to be used. How many AND gates to be used is multiplicand and multiplier. You need to do multiplication m into n. So m is what? 4, and n is what? 4. M into n. So you will be getting 2 into 2. You will be getting total 4 AND gates. You need to use total 4 AND gates. Like let me show in this case. This is 1, 2, 3, and 4. So we need to use 4 AND gates. You need to use 4 AND gates, and the output of this AND gate will be single. See here, so this the output of this AND gate will be single bit. So let us consider A0 as 0 and B1 as 1, so that the output from this is 0. And next is both are 1. Let us suppose the output from this will be uh, the output from this will be 1. Why? Because there is an AND gate. So AND 1 into 1 will be 1. So there will be two inputs. Concentrate. There are two inputs, and output is what? The output will be a sum and a carry. Sum will be placed in P1, and carry we will be using as a next operand. We will be using as a next operand for doing addition. So in this case, can we use half adder? Can anyone? Yes. So one is I'm using AND gate. One is I'm using AND gate for representing this between A naught B naught, A naught B1, A1 B1, A A1 B1, A1 B naught. Okay. Next, after representing an AND gate, you will be getting output from this AND gate as single bit. Okay. So from this output, you will be getting a single bit. From this also, you will be getting a single bit. This two you need to send to what? This two has to be what we need to do. This two addition or multiplication between these two, ma? Answer please. In this two, what we need to do? Addition or multiplication? This two, we need to do addition, right? So for this addition, which circuit to be selected is the half adder. So half adder, it takes two inputs. It generates a sum and a carry. Sum is placed in P1, carry is given for the next. So next addition, next half adder input will be what? This is your half adder. Now tell me the input for half adder for this one. What is one input? One input is
C1.
one input good. One input is C1, and the other input is what? The output of AND gate. The output of AND gate. What are the two inputs of this AND gate? What are the two inputs of this AND gate? One is
A1 B1.
A1 B1, and the other operand is C1. So that you will be getting out what output for half adder? One is sum and the other one is carry. This sum will be considered as P2. This sum will be considered as P2. This carry will be considered, again this carry we are giving here, and this carry will be considered as P3. This carry will be considered as P3. Okay. Now I will show directly the diagram. So before that, for implementing this circuit, we are using how many AND gates? The formula is m into n. So let us suppose I will show one more example. This is a case. Okay. So this is a question given as multiplicand 4 bits, multiplier 3 bits. Okay. Now tell me how many AND gates required for this. Consider this as m and this as n. So how many AND gates required, ma? M
12.
into n. So total
12.
12.
12.
12 AND gates required. Now tell me how many product terms will you get from this output? How many product terms?
7.
7 product terms. Yes, good. So we will be getting 7 product terms. So what are those product terms? from P0 to P6. As we have started with 0, we'll be ending with P6. Okay. So this is the fun. So before going, but in this case, we will be not using a half adder. We need to go for full adder. Why? Because 4-bit. So in which case you will be going for 4-bit means for a full adder. So in a full adder, what we are simple for A as 4 bits, B as 4 bits, we'll be going for 4-bit binary adder. So we'll be going for 4-bit binary adder that I will show later. But let me complete this example. Okay. So until this, everyone clear, ma? Then I will go for circuit diagram. This is a general process. Based on this, we need to go for designing a circuit. So here there is two AND gates. For this AND gate, I'm representing this AND gate as, we'll be having two AND gates. Okay. Next is what? So what is common? A0 is common, right? So what I'm doing is I'm just giving as a A0. Next one operand as B1, and this has to be connected to A0. And the other operand is what, ma? B1. The other operand is what? Other operand is what?
A0.
B0. Okay. Next, our main target is to find out P0, P1, P2, P3. Okay. So P0 I need to get directly. Why? Because this is the output. So the output of this AND gate is P0. Okay, completed. Next is what? Let me take the other two AND gates also. So I'm taking the other two AND gates and the other two AND gates. For those two AND gates, which one is common, ma? Which one is common?
A1.
A1 is common. So let me connect this to this also. Next is the two which are, one is B0 and the other one is B1. And the other one is B1. Okay. Now what I have to do, for this two, I said already you have to select what? Half adder. For this two, we need to select half adder. So where is this AND gate, ma'am? A0, B1. This is your AND gate. And the other AND gate is what? A1, B0. Where is A1, B0? This is your A1. This is your A1, B0. So this is your AND gate. So I need to connect this two as which circuit, ma? I need to connect this two. There is a plus. So I need to connect to. I need to connect this two to half adder or full adder.
Half adder.
So I need to connect this to half adder, and the output generated will be, one is sum and the other one is carry. This sum I'm connecting to which product? P1, and this carry. So next is what? Next is A1 B1. So this is your A1 B1 as one operand, and the other one is C. Okay. So this is your C. We are taking this two and we are connecting to half adder. We are connecting to half adder, and the output from this will be, one is sum and the other one is carry. Okay. So this is your P1, and this sum, the output of this is sum. So this is stored in a P2, product P2, and this carry is P3. This carry is P3. So in this way, we are designing a multiplier. So see here, ma'am. So is this the same diagram? Yes. Okay. So what we have done, we have considered A0, B0, B1, two AND gates, and one AND gate, first AND gate we are directly giving as a P0. So we are directly giving as P0. Next two AND gates, this and this AND gate. If this is clear, then you representing a logic diagram is very easy. Okay, next is what? A0 B1 AND gate and A1 B0 AND gate. You need to connect to half adder. So A0 B1 and A1 B0 we are connecting to half adder. So this is your half adder. So from this you will be getting output sum and the carry. Sum we are giving to product P1. This is your final products, and carry will be giving as one more operand. This is your carry, and next is last operand is what? A1 B1. So this is your A1 B1 and this is your carry. Both you will be getting output sum and carry. Sum we are giving to P2, carry we are giving to P2. So this is your 2 bits 2 into 2 binary multiplier. Now let me take an example. So let me take 1 1 and let me take one example. Okay, so one example is 1 1 1 0. Okay, 1 1 1 0, I want to do multiplication. So for doing multiplication, the 0 must be multiplied with 1 and 1. So 0 into 1 and 0 into this one 1. Next is 1 bit position you need to shift. Next is 1 into 1 and 1 into 1. So you will be getting what? So we are taking directly this as P naught. So for P naught you will be getting what? 0 into 1 is 0 or 1? So 0 you are directly taking AND gate output. In this case the output is what? 0. In this case the output is what? 1. 0 plus 1 is what?
1.
1. So in this case you need to take directly as 1 into 1 is what? From this case, one operand is 1 into 1 AND gate and the other is carry. So what, is there any carry generated? No. So 0. 0 plus output of this AND gate, 0 plus 1. So you will be getting 1. Okay. So the carry generated in this case is 0. So P3 will be 0. So what is the answer? 0 1 1 0 is which number is this? It is 6. Means what we have considered, 1 is 3 into we consider 2. Is it, are you getting 6? Yes, you are getting 6. So in this way, for representing partial terms, we need to represent AND gate, and for adding those two, we need to use based on how many inputs you are giving. So as there are 2 inputs and 2 outputs, so you are selecting half adder. So this is your half adder representation. This is your representation of half adder. Okay. Now let me go for the other example. Okay. So let me go for the other example. The other example is 4-bit multiplicand and 3-bit multiplier. Okay. Why it is not erasing? Okay. In this case, so in this case, we are going B0, B1, B2, B3. Okay. So this has to be multiplied with B0, B1, B2, B3. A0, B0, A0 will be common. Why? Because this has to be multiplied. So A0, B0, A0, B1, A0, B2 and shift it. So for the next one, A1, B0, A1, B1, A1, B2, A1, B3, A1, B0, next. Next again it has to be shifted one bit. Next is A2. So A2, B0, A2, B1, A2, B2, A3, B3. Okay. Now is a question that how to implement this circuit. So done this, everything is clear, right? So we have done this. Now the second question is how to represent. First, you must know how many AND gates required for this. Can anyone tell me how many AND gates required? M into N. How many AND gates required actually totally? 12.
12.
12 AND gates. Okay. So 12 AND gates required. And in this, the total product terms M plus N. So you will get 7 product terms. 7 product terms. And now how to do is, we are doing how many bits of summa? See here, the first one, concentrate in this diagram only. The first one we are giving as it is. The first one we are giving as it is to P naught. Okay. So how many bits are there? The second we have 4 bits. 1, 2, 3, 4. But in the first one, as the first least significant bit we have given for the product P0, we have the other operand. Means what? Let me show this example. So when 4-bit binary adder, you will be having 4 inputs as A and 4 inputs as B, and you will be getting what output? You will be getting output what, ma? Sum. Okay. Sum is S0, S1, S2, S3, and you will be having a carry also. Carry C4 if it is starting with C0. Okay. So totally you can consider as how many bits including carry? Output of this including carry. How many bits you can consider? Including carry. Leave about this, ma. What I am asking 4-bit binary adder. So if 4-bit binary adder, you will be adding 4 bits A and 4 bits B, and the result generated is 4 bit sum. And if there is carry generated, total you will be having output how many bits including carry?
5.
5
5.
bits.
Okay, 5 bits, right? So now think about this. Concentrate, think about this. So 1 bit I have given here. Okay, if you give 1 bit here, so next what you can do, so in this place in order to do this, I am giving one operand as in the most significant bit I am placing 0. So in this place I am placing 0. So why? Because there is no AND gate here. So why? Because in this one operand I have given directly, we are not doing any sum for that. So we have given directly, the other operand we are placing 0. Okay. So now for one this. Uh, okay, so for this what I'm doing, this is your 4-bit adder, concentrate. This is your 4-bit adder. So in this 4-bit adder, what are those 4 inputs, ma'am? This 4 inputs. One AND gate, second AND gate, third AND gate, the output of this. Okay, so these are what? One is A0B1, one is A0B1, and the other one is A0B2, and the other one is A0 B3. Okay. Next we for A we need 4 inputs, right? In this only 3 are there. So the other one we need to place a 0. So this is 0. And the rest of the 4 are A1 B0. Cheppandamma. Rest of the 4 are A1 B0, A1
A1
B1,
B1,
A1 B2,
A1 B2, A1 B3.
A1 B3. So the output from this will be what? S0, S1, S2, S3, right? So the output from this is what? You will be getting S0, S1, S2, S3. Okay. So the output from this will be S0, S1, S2, S3. In this also, S1 we are giving directly, concentrate. In this also, S0 we are giving directly to P1. Okay. So next is what? Again, in this sum, we are giving this as P1. This we have one more AND gate here. What is that combination, ma? A0? A0? What is this AND gate? A0? What AND gate we left, ma? Only we
A0
A0,
B0.
B0. This we have considered what? Directly as P0. And next, the sum S0 will be considered as P1. Next, for getting P2, this is your P2, and this is your P3, this is your P4. Okay, so this is your until S3 P4. Now for getting P P5, what we are doing now? What we are doing? Can anyone? What will be this side? We have three, S1, S2, S3. Okay, and you can give here as a carry. You can give here as the carry from this. Okay, if carry is there, then we have to place, or else it will be, if carry is 0, you will be placing 0. Okay, you will be placing 0. Again, next full, I want an answer, ma, for the next full adder. So how many, what will be the A values and what will be the B values? Answer, I will ask. Okay, so the B operands are ready here. What are those? A2 B0, A2 B1, A2 B2, A2 B3. Okay, so this is your B. Can anyone tell me what is A? A is what? The output from this. So S not already given to P1. So remaining will be what? S1,
S2,
S2,
S3.
S3, and this one is what?
0.
0, but you should not mention as 0. It should be given as
Carry.
carry. Good, good. So this should be given as carry. Why? Because I already discussed, if the output from this 4 bit will be 5 bits, 4 bits from sum, 1 bit from carry. So if this first bit, if you are removing 5 minus 1, you will be getting 4 bits, including a carry. So you are adding C here. So finally, you will be getting again 4 outputs. Okay, you will be getting 4 outputs in that output. So where are this? Okay, this one directly we have considered. Next is S1 and A2 B0 you are considered as P2, next as P3, next as P4, P5, and the first last carry we are considered as P6. I will show with the diagram. Okay. So first, before that, you need to show that the number of AND gates used will be, where is this cursor? Number of AND gates used between in this circuit is 4 into 3. You will be using total 12 AND gates. You will be using total 12 AND gates, and number of what? Number of product terms is what? Number of product terms is what? M plus N. So you will be getting how many more? Number of product terms total 4 plus 3, you will be getting total 7. So these are the total 7. Okay. So let me trace. So this is your 4 operands. These are your 4 operands, B0, A0, B0, this 4. So B0 is common in this. Okay. So B0 is common. Okay. So B0 is common, and the remaining is A0, A1, A2, A3. Okay. So this is, I already said that in this, the first one will be given directly to P0. So according to this diagram, so the first and we are giving directly to P0. So as for this AND gate, we are directly giving to P0. Okay. So remaining will be only 3, but we need 4 bits. 4 bits A, 4 bits B. So as we left out with 3 bits, what we are doing, we are adding 0, 0 in the most significant bit. So if you add 0, the meaning will not change, as we already discussed. If it is 1, 0, even if you add 0 here, it will be 2 only. Even if you add one more 0 also, it will be 2 only. So in this case, we have converted the 3 bits to 4 bits by applying a 0 here. Why? Because initially you will not have any carry for keeping there. So you will be placing 0, and you are doing addition, 4-bit binary adder. After doing 4-bit binary adder, you will be getting 4 sums and 1 carry. See here. So 4-bit sum and 1 carry out. So in this first sum, according to this diagram, the first sum we have given to P1. Okay, the first sum S0 we are given to P1. Okay, so next is what? S1, S2, S3 and carry out. So S1, are we doing 4 by 3 or 3 by 4, ma?
4 by 3, ma'am.
Are we doing 4 by 3 or 4 by 4? Okay. So
4
this
by
one,
3.
yes, 4 by 3. So in this, what we are doing? So in this case, this completed by placing 0 in this case. This one we have considered as P0. So this one we have given P0, and the output from this you will be getting S0, S1, S2, S3 and the carry out. So S0 it is given. So the remaining will be S1, S2, S3, carry out. And the other bits is what? The other bits is what? The other bits is this 4 bits. This 4 bits, S1, S2, S3 and C. Okay. Yes, S1, S2, S3 and C, and the other one is this gates. A2 is common in this. You try to see, yes, A2 is common in this, and the remaining is B0, B1, B2, B3 and gate. So from this output, you will be getting 4 sums again. S1, S2, S3, S4. We are giving to P2, P3, P4, P5, and from this output, you will be generating a carry out. Carry out is given to P6. Okay, carry out is given to P6. So total we'll be having 4 by 3 means, first you, before drawing, you must know that there are 12 AND gates required and the product will be 4 plus 3. So you will be using total 7 products. You will be using 7 products, and as there are 4 inputs and 4 inputs, we are using 4-bit binary adder. Same will be for 4 by 4 also. Same will be for 4 by 5 binary multiplier. So 4 by 4 binary multiplier, what we are doing is same. So one more will be added, one more will be added. Let me show this also, so that even if any question comes, it will be easy for you to understand. A0, A1, A2, A3 multiplicand, B0, B1, B2, B3 multiplier. Okay, so what we are doing, A0, B0, A0, B0, A1, B0, A2, B0, A3. We are doing this one, first one. Okay, first this one is completed. Next, in order to do this, in the next left shift you need to do. So you need to start from here. So B1, A0, B1, A1, B1, A2, B1, A3 until this one. Okay, now this should be directly considered. This should be, you need to do what? The sum of this will be taken as P1, and the sum of this, will be considered as P2. Okay, so by saying this, tell me how many AND gates required for 4 by 4 binary multiplier. How many AND gates required?
16.
Yes, good. So
16.
we require 16 AND gates. And tell me how many products we need. How many products? M plus
8.
N.
8, ma'am.
8 products. Okay. So 8 products. So this is your final diagram. So you see this, so that you can draw the diagram easily. Don't try to by hand the diagram. See the concept. So in this case, what we have first, you try to complete an AND gates. So I will show without this. I will show more, just a minute. Hmm. Okay. So first we will construct this 4 AND gates. So B0 is common. So B0, as we have started with B0 multiplied with all, so you will be having B0. So I'm starting with AND gate, 4 AND gates, 4 AND gates. In that, B0 is common. B0. Okay. So next, this one and this 4 AND gates. So I will take 4 AND gates again. With what will be common in this one? B. What will be common in this? The second one. B. In common.
B1.
B1. So B1 is common, and remaining will be A0, A1, A2, A3. This here also the other operand will be, connect one operand to B0, and the other operand will be, A0, A1, A2, A3. Now I want an answer by seeing this question. So first, the output of this AND gate given to P. So directly this is the output of this, and A0 B0 directly I am giving to P0. Next is what? Next is A0 1 2 A1 A2 A3 and B1. This we are giving for 4-bit binary adder. So in this case, you try to select a 4-bit binary, 4-bit binary adder, 4-bit binary adder. In this case, you have 4 bits, but in this case, you have 3. The other bit where you will place, will you add here, right side or left side?
Left side.
Left
Most,
side, ma'am.
most significant bit position, you will add 0, so that this part will be completed. So once this part completes, so you will be getting output what? 5 and 4 are output, including carry. Including carry, you will be getting the output of this 4-bit binary adder. Is it 5 or 4-bit including carry?
5.
5. So 5. In that 5, this is your S0, S1, S2, S3, and this is your carry. So in this next step is what? This and the output of this S0 we are giving directly to P1. So this is your output we are giving directly to P1. Completed. Next is what? Next is S1, S2, S3 and carry and B2 and the other combinations with A. So what I need to do? I need to consider again 4 and 4 and in that which one is common ma? B?
B2.
B2 is common. So this has to be connected to one operand for and the other operand. Other is what? A0, A1, A2, A3. So this one you are getting 4. In this also you are getting 4. You are doing again 4 bits. You are getting again 4 bit. So in this 4 bit again, this sum we are giving to what ma? The sum we are giving to P2. So see here. So this sum, the output of that sum, see here. Until here I have done. Let me complete. So where I am. Now tell me what we will be getting the output of this 4-bit binary adder. 4-bit binary adder. Tell me the output of 4-bit binary adder, ma? 5 bits, right? So in this 5 bits, again you will be getting S0, S1, S2, S3, and carry. In this one will be given to this one. The most S0 will be given
P2.
to P2. Again this 4 and next 4 AND gates are what now? Uh, in that which one, what is common?
B3 no.
B3.
B3 is common and try to connect with the other candidates and the other inputs will be A0, A0, A1, A2, A3 and from this 4 and including carry this 4 will be given to again a 4 bit. Finally you will be getting 5 outputs. So this will become P3, P4, P5, P6, P7. Okay, 5 వచ్చాయా 1 2 3 4 5. Yes, so you'll be getting total products 8. So this is the actual diagram. See, this is the diagram. Okay, so there is no need of by adding. Just if you know this, if this process, if you know, based on this process you can construct your logic diagram. Is it clear, ma everyone? Binary multiply